Hey, physicists! David here. Our brains are incredibly intricate things. They need to operate an entire body, absorbing and processing our environment, all while giving us the freedom to think and say, and do a wide variety of things. A complex collection of atoms give rise to ideas and have allowed creatures like us to accomplish tremendous feats. We can do all sorts of things, like retain and apply vast amounts of information. We can apply this to something like debating whether or not pineapple belongs on pizza. Or we can even construct other things to think for us so we no longer have to. These thinkers are called computers, and they're special in that they are digital versions of the thing that pilots our meat-shielded bone necks, also known as a brain. Brains are amazing. They're comprised of over 100 billion neurons. Each neuron can fire roughly 200 times every second, and there are a total of 100 trillion synapses between them. Rudimentary estimates would say that the brain can perform roughly 10 to the 15th logical operations every second. That's roughly a petaflop. There are supercomputers out there that can run this quickly. One example being Blue Waters, a computer that can run at this speed and can go up to even 13 petaflops. However, it consumes roughly 15 megawatts of energy to operate, and it takes up roughly a football field. For comparison, your brain is roughly the size of a football and only consumes 15 watts of energy at any given time. Surely, there's no possible way for a human-sized computer to simulate the brain. Or is there? Let us look at the Josephson Junction. It is a component of a circuit that utilizes quantum mechanical effects to operate. This junction is comprised of two superconducting materials bridged by something that does not superconduct. Normally, for a circuit, the current is driven by a potential difference, a voltage, but here that is not the case. There is quantum tunneling between specific types of electrons known as Cooper pairs, and this tunneling does not depend on the voltage, but rather the phase between the two conductors. This means that, no matter what, there is a continuous current between them, and examining their behavior of the phase through a very specific type of junction known as a resistively and capacitively shunted junction, one can find that this can be simplified down to a damped pendulum. But why would this be helpful? Well, if we can assemble these junctions into a specific circuit shown here, we can couple them to each other. And solving for the relative phases of the junctions with respect to time, we can see that they have a profile that mimics the firing of a neuron. In the pendulum analogy, this is like a double pendulum undergoing something called a phase slip by completing a rotation. But surely this is going to lead to the same issue as before, where we would need a room filled with these junctions, consuming massive amounts of energy to try and come close to simulating a brain. But no! This problem has attempted to be solved by trying to directly model a neuron in circuitry. These could then be connected to each other to form the brain in a single circuit board. However, this smaller scale has had a direct impact on its performance. The fastest of these models can manage a single gigaflop for a single neuron, but this drops down to 0.1 megaflops when they're connected to 1,000 other neurons, which is much like the density of our own brains. This is because they're limited by how fast these simulated neurons can fire and communicate with each other. However, a Josephson junction can fire their simulated neurons in roughly 50 picoseconds. When densely connected, they'd be able to manage 20 gigaflops even for the dense network. Sure, this is still 5 orders of magnitude slower than the theoretical limit of an actual brain, but this would not take up 400,000 times more space than your brain does. Utilizing these junctions, we could easily smash the ceiling that current neuron simulations perform at without needing so much energy and space to operate. And now imagine what would happen if the system was expanded all the way up to that size as well. My goal is to computationally show that these junctions in action can create a simplistic neural network. This would be done by taking the damped pendulum and solving it numerically using Newton's method. Then, by coupling them, I can create the action potentials of the neurons, and then all that's left to do is combine them in a way that they can communicate with each other, forming a simplistic network shown here. This could then be applied physically with these neurons in circuitry, and it would be easy too, as single chips have already been shown to be able to easily house 1,000 of these junction pairs. I'll be demonstrating this on a Raspberry Pi 4, which goes to show you that you don't need a supercomputer of your own to demonstrate the potential of the Josephson junction. Maybe one day you'll be able to run a physical network yourself on something as big as a Pi, but that, dear viewer, is up to you to make a reality. The prospect of computers being able to readily simulate biological neural networks will rapidly accelerate the development of intelligence of the computers, as it will become much more accessible to scientists around the world. What can we do with machines that hold such prowess? One day, we may be finally able to communicate with a computer that can think, talk, and feel. They'd be able to ponder the very nature of the universe with us, and hopefully help us answer some of life's greatest mysteries. Hopefully they can finally answer, does pineapple belong on pizza? And as always, thanks for watching.